Hi, welcome to our channel of IGNOU audiobooks. Indira Gandhi National Open University, School of Agriculture, SOA, Master's Degree Programs, Master of Science in Food Safety and Quality Management, MSCFSQM, Second Year MVP 005 Food Toxicology and Public Health Block-1 Introduction to Food Toxicology, Unit-1 Basics of Food Toxicology 1.0 Objectives. After reading this unit, you will be able to explain importance of studying the food toxicology, define the basic terminologies used in the field of food toxicology, discuss the general principles of food toxicology, classify toxicants, narrate chemical and biological aspects of injurious substances present in food, identify the effects of food toxicants on human health, and explain the concept of food safety risk management. 1.1 Introduction. The science of toxicology has flourished from its early origins in myth and superstition, and is of increasing importance to many aspects of modern life. Food toxicology is concerned with assessing injurious effects of chemicals present in food on living systems, in particular human beings. The chemical agents can be man-made, such as pesticide residues, food additives, contaminants originating with processing machinery or packaging material, or of natural origin like bacteria, virus, fungi. They can also be generated during course of preparing, processing and preserving food. It also includes investigations of food additives, migration of chemicals from packaging into food, and persistence of feed and food contaminants in food products. Finally, because the study of food has obvious social implications, it is obligatory to examine the risk and take appropriate steps to reduce/nullify the risk by adopting stringent regulatory measures. Thus, food toxicology and safety cannot be completed/said to be related to the common man without regulatory system in place. For example, considering the risk of presence of contaminants and toxins in the food and probable exposure conditions to the population, regulatory bodies such as United States Food and Drugs Administration, US FDA, and Food Safety and Standards Authority of India, FSI, sets in regulations and guidelines to safeguard public health/consumer safety. In view of this, we shall understand why food toxicology is a unique branch of toxicology, classification toxicants, factors affecting toxicity of compounds, and how risk analysis principles are used in toxicology to set maximum limits/maximum residue limits/levels, MRLs, for pesticides, drugs, contaminants present in our food. 1.2 Definitions. Toxicology is the science of poisons, toxicants or toxins. It can also be defined as the science that deals with adverse effects of chemicals on living systems/organisms, or it is study of poisons that include their physical and chemical properties, detection and identification, biological effects, treatment and prevention of disease conditions produced by them. Toxicology in the present century continued to develop and expand by assimilating knowledge and techniques from most branches of biology, chemistry, mathematics, and physics. A recent addition to the field of toxicology, 1975 to the present, is the application of the discipline to safety evaluation and risk assessment. There are several sub-branches of toxicology such as food toxicology, environmental toxicology, ecotoxicology, forensic toxicology, occupational toxicology, veterinary toxicology, regulatory toxicology, etc. Based on target organ/systems, the branches are neurotoxicology, immunotoxicology, genetic toxicology, reproductive toxicology, etc. based on response, effect, observed/obtained. The sub-branches are teratology, evaluates defects in newborn fetus when pregnant mothers consume/exposed to a toxicant, and carcinogenesis, ultimate toxic effect of many chemicals owing to long-term or chronic exposure. Food toxicology. Food toxicology is a distinct discipline of toxicology that evaluates effects of components of complex chemical matrix of the diet on the activities of toxic agents that may be natural endogenous products or may be introduced from contaminating organisms or from food production, processing, preparation and storage. Few other definitions related to toxicology are regulatory toxicology. It includes collection, processing, and evaluation of epidemiological and experimental toxicology data to permit scientifically based decisions directed toward the protection of humans from the harmful effects of chemical substances. This area of toxicology is involved in the development of standard protocols and new testing methods to continuously improve the scientific basis for decision-making processes. Examples: US FDA, FSI xenobiotic. It is any substance harmful or not that is foreign to the body. Toxicokinetics, the study of absorption, distribution, metabolism and excretion, ADME, of toxicants in the body. ADME is also known as kinetics. Toxicodynamics, the study of biochemical and physiological effects of toxicants and their mechanisms of action. Toxicodynamics helps us understand how a chemical is producing toxic effect, e.g., mycotoxin. Aflatoxin produces liver tumors. The mechanism of how it causes liver tumors is studied so that we can find out intervention strategies, treatment and prevention, and avoid formation of such tumors. Poison. A poison is any substance or matter which when applied either externally or internally produces ill effects on health or entirely destroys the life. Whether a substance is a poison or not depends on many factors, viz., dose, species, route of exposure, etc. Toxicant. Toxicant term is synonymous with poison and is a more professional term. Types of toxicant toxins. These are special types of poisons that are produced by living organisms in small quantities, also called as biotoxins. Few examples are mentioned below: phytotoxins, toxins produced by plants, mycotoxins, toxins produced by fungi, zootoxins, toxin produced by lower animals, e.g., bufotoxin produced by toxic toad bacteria, toxins produced by bacteria, either endotoxins or exotoxins. Toxicity, the potential of a chemical to induce an adverse effect in the living organism. Toxicosis, it is the condition or disease state that results from exposure to a toxicant. Term toxicosis is often used interchangeably with the term poisoning/intoxication. Types of toxicity. Toxicity of a chemical or toxicity studies are either conducted in vitro, in a single cell, single tissue or cell lines, and or in vivo, in an animal model system, mostly done on laboratory animals such as rodents, guinea pigs, hamsters, rabbits, dogs, and primates, etc. Acute toxicity, study of toxic effects produced by a single large dose or multiple doses during 24 hours period. Subacute toxicity, study of repeated exposure of a toxicant and its effects for a period 30 days or less. Subchronic toxicity, study of repeated exposure of a toxicant and its effects for a period of 1 to 3 months. Chronic toxicity, study of repeated exposure of a toxicant and its effects for a period greater than 90 days. Generally, these studies are conducted for 1 year or 2 years. The carcinogenic potential of a substance is evaluated in a chronic toxicity studies typically conducted for a period of 1 or 2 years. A chemical/substance can produce either of the above effects depending on the exposure period. For example, benzene given in an acute dose causes central nervous system depression, while in chronic dose produces leukemia, blood cancer. Dose and associated terms. Dose is the total or absolute quantity/amount of a substance applied or administered all at one time to an individual to get desired pharmacological or toxicological response. Dose is expressed in mg/kg body weight response. The effect obtained/seen after exposure to the dose of a chemical/toxicant/a drug or medicine. There are molecular sites, receptors, with which chemical interacts to produce a response. An intensity of response is related, directly proportional to the concentration of a substance at active site, which in turn is related, directly proportional to the dose of a substance administered. Generally, more the dose is, more is the response/toxicity. The response is dependent on environmental concentration of a substance/toxicant properties of the toxicant, frequency of exposure, length of exposure, exposure pathway, tolerance, state of decreased responsiveness to the toxic effect of a chemical resulting from prior exposure to that chemical or to a structurally related chemical. Lethal dose. It is the lowest dose that causes death in any animal during experimental period. Lethal dose 50/median lethal dose, LD50, dose of a toxicant that is lethal, kills/causing death to 50% of the population exposed to it under experimentally defined conditions like species, route of exposure and duration of exposure. It is expressed in mg/kg body weight. It is a commonly used measure of toxicity. Different toxicants can be compared based on LD50. Lowest dose is the most potent one. LD50 indicates nothing about the non-lethal toxic effects of a compound. A chemical may have a large LD50, but may produce illness at very small exposure levels. It is incorrect to say that chemicals with small LD50 are more dangerous than chemicals with large LD50. They are simply more toxic. The danger or risk of adverse effect of chemicals is mostly determined by how they are used, and not by the inherent toxicity of the chemical itself. Comparison of toxicants based on LD50. LD50 and toxicity level less than or equal to 1 mg/kg, extremely toxic 1 to 50 mg/kg, highly toxic 50 to 500 mg/kg, moderately toxic greater than 500 mg/kg, toxic 500 to 5000 mg/kg, slightly toxic greater than 5000 mg/kg, practically non-toxic. Lethal concentration, LC. It is the lowest concentration of a compound in feed, or in water in case of fish, that causes death. Expressed as mg/kg of feed, or water, lethal concentration 50, LC50. The concentration of a compound/toxicant in the feed or water that is lethal to 50% of the exposed population. 1.3 Uniqueness of food toxicology. The nature of the food itself attributes to the uniqueness of food toxicology. Food occupies a central position in all the cultures since it cannot be produced under definable environment in controlled conditions. Source of food. The fact that food is harvested from highly diverse sources like the soil, the sea, inland waters, or is derived from the land animals, which are subject to unpredictable forces of nature, makes the constancy of raw food unreliable. The narrow margin of amount required for the essential nutrients to prevent deficiencies and toxicity, overdose. Food also acquires uniqueness from the presence of certain nutrients, like vitamins. Especially some of them like vitamin A may be toxic at a level just tenfold above the levels required to prevent deficiencies. Food ingredients. Evaluation of food ingredients often rely on reasoning unique to the food science in a sense that such substances may be normal constituents of the food or modified constituents of the food. When the safety of such substances is assessed, it focuses on digestion and metabolism occurring in the GI tract. In most of the cases, products of that food ingredients are absorbed. These products may be identical to those derived from natural products. Kidney diseases decrease the drug or xenobiotics clearance, causing uremia. Similarly, cardiovascular diseases, neurological disturbances, respiratory diseases affect metabolism and elimination of ingredients of food or their metabolites/breakdown products. Food generally cannot meet the rigorous standards of chemical identity, purity and good manufacturing practices, GMP, met by other consumer products. Moreover, most foods cannot be commercially produced in a definable environment under strict quality controls. Food is an exceedingly complex mixture of nutrient and non-nutrient substances, whether it is consumed in the natural, unprocessed form or as a highly processed ready-to-eat meal. This can be better understood in the subsection below. Nature and complexity of food. Food is usually of plant, animal, or fungal origin, and contains essential nutrients, such as carbohydrates, fats, proteins, vitamins, or minerals. The substance is ingested by an organism and assimilated by the organism's cells to provide energy, maintain life, or stimulate growth. Table 1.1. Food as a complex mixture: nutrients, carbohydrates, protein, lipids, minerals and vitamins. Non-nutrients: naturally occurring substances, food additives, containers and product of food processing. Food also contain non-nutrients/anti-nutrients/anti-nutritional factors which are contributed by the nature as well as they could be formed during processing. Some of these substances may be anti-nutrients such as trypsin and or chymotrypsin inhibitors in soybean, affecting protein digestibility/absorption, lectins in legumes and phytates in millets. Soybeans and other cereals binds with minerals and make them unavailable for the body cells, causing mineral deficiency. Saponins in soybeans affect absorption of vitamins A and E and of lipids. During processing of food, non-nutrient substances also get added. They are formed due to heating/other processes. 1.4 General Principles of Food Toxicology. Potency: although all substances exhibit toxic and lethal dose-response behavior, there is a wide range of LD50 values for toxic substances which decides their potency. Substances with LD50 value more than 2 grams/kg body weight, BW, are considered to be slightly toxic and relatively require large dose in range of 1 cup to produce lethal effects in an adult human being. However, substances with LD50 value less than 1 mg/kg requires only few drops or less to produce a lethal effect. Substances/chemicals having low LD50 are highly potent. Thus, potency is inversely proportional to the toxicity/toxic effects. Look at the screen. Homeostasis dose-response phenomenon characterized by beneficial effect at low dose and toxic effects at high dose. Some substances required for normal physiological function and survival exhibit homeostatic dose-response behavior, for example vitamins. At very low dose, there is a deficiency and with increase in the dose, beneficial effects are produced. However, high dose results into toxicity. For example, high doses of vitamin A can cause liver toxicity and birth defects, while vitamin A deficiency contributes to the blindness and increases the risk of disease and death from severe infections. There is just a 10-fold margin between the dose of vitamin A that is required to prevent deficiency and produce toxic effects. Shibamoto, T., and Bjeldames, L. F. 2009. Principles of Toxicology. In Introduction to Food Toxicology. pp. 9. Elsevier role of ADME/toxicokinetics in influencing response. As you have read above in the toxicokinetics definition, ADME plays an important role in influencing good/adverse, toxic, response on exposure to any chemical/food. You will learn in detail about importance of ADME of a toxicant/chemical in the next unit, i.e., Unit 2. Margin of safety, RD/TDI, MRL. Safety is defined as freedom from danger, injury, or damage. Absolute safety of a substance cannot be proven since proof of safety is based on negative evidence, or the lack of harm or damage caused by the substance. The range of dose is referred to as margin of safety of drug/chemical. The margin of safety of a chemical is a concept that tells us how safely we can use a chemical for good purpose without risking too many adverse effects at the same time. Following definitions are needed to understand by the students. Maximum residue limit/maximum residue level, MRL. It is the maximum amount of a pesticide or drug, mainly veterinary or pharmaceutical, residue that is legally permitted or recognized as acceptable in or on food commodities and animal feeds. Maximum residue limit term is used for pesticide residue. Maximum residue level term is used for drug residue. Regulatory bodies set up MRL/maximum limits for the toxins, contaminants and residues present in our food or for the ones that can be introduced in the food through processing, handling, storage, etc. No observed adverse effect level. No IL. The highest dose of a substance that under defined conditions of exposure causes no observable/detectable adverse effect on the morphology, functional capacity, growth, development or lifespan of the test animals. Unit of NOIL is mg/kg body weight. NOIL value is used as the basis for setting human safety standards for chemicals present in our diet such as tolerable daily intake, TDI, or acceptable daily intake, ADI. NOIL is a variant of a NOIL that specifies only that the effect in question is adverse. Acceptable daily intake, ADI. It is the daily intake of a particular chemical in food/water, which during a lifetime span will not induce any adverse effects in an individual, human being. Unit of ADI is mg/kg/day. Tolerable daily intake, TDI. It is similar to ADI but is typically used for food contaminants. ADI or TDI equals NOIL divided by UF1 into UF2 where UF1, uncertainty factor for extrapolations from the animal or model system to humans, UF2, uncertainty factor for inter-individual variability in the human species. ADI is used for food additives and residues, while TDI is used for contaminants and toxins. Lowest observed adverse effect level, ROYAL. It is the lowest dose at which the toxicity is produced. Margin of safety, MS, equals LD1. ED99. LD1 is the 1% lethal dose level and ED99 is the 99% effective dose level. A less desirable measure of the relative safety of a substance is the therapeutic index 1.5 classification of toxicants. Potential sources of toxicants in food include nutrients, natural food toxicants, contaminants, and chemicals or substances intentionally added to food. Food additives. Toxic agents are classified in a variety of ways, depending on the interest and needs of the classifier. A. Natural food toxicants. 1. Allergens, food allergens. 2. Plant toxins/phytotoxins. 3. Mycotoxins and mushroom toxins. 4. Marine toxins, seafood toxins, also known as phycotoxins. 5. Heavy metals, typically considered as contaminants. 6. Bacterial toxins, botulinum, S. aureus, B. cereus, B. Contaminants in food. 1. Pesticide residues. 2. Antibiotics and veterinary drug residues. 3. Heavy metals. 4. Environmental pollutants, dioxins, phthalates, persistent organic pollutants, POPs, etc. 5. Bacterial toxins. C. Substances added to food. 1. Food additives. D. Toxicants generated during food processing. 1. Acrylamide. 2. Polycyclic aromatic hydrocarbons, benzopyrene. 3. Polycyclic aromatic amines. 4. Nitrosamines. 5. Maillard reaction products. 1.6 Sensitivity of humans to chemicals/toxic compounds in food. Some people are highly sensitive than the rest of the population to a particular type of food/ingredients of a food/additives present in the food. Reaction to food is exhibited in various forms and several symptoms are visible, and if not treated in time, person can even die. Body's immune system is activated due to exposure to food ingredients. Allergens present in the food, such as peanut allergy/fish or shellfish allergy. Allergy is a general term meaning clinically abnormal response attributed to an ingested food or food additive. It is a pathological reaction resulting from ingestion of food. Some people exhibit allergy or food hypersensitivity. Hypersensitivity may not be immunologically mediated, but food allergies are always based on immune response. It involves IgA antibody. Food allergic reactions may occur in few individuals only after small amount of substance is ingested and is unrelated to any physiological effect. It is an immune-mediated, cellular or humoral response, requires prior exposure to antigen or cross-reacting antigen.
Food allergy and hypersensitivity has been covered in detail in Unit Note. 4. Food anaphylaxis is another term which represents classic allergic hypersensitivity. Reaction to food or food additives. A humoral immune response most often involves IgE, antibody, and release of chemical mediators. It may result in death if not treated immediately. This type of reaction may involve non-immune release of chemical mediators. As like anaphylaxis reaction, another reaction called as anaphylactoid reaction to food is also reported. It is an anaphylaxis-like reaction to a food or food additive as a result of non-immune release of chemical mediators. This reaction mimics the anaphylaxis but it is non-immune mediated. 1.7 Factors affecting toxicity of compounds. There are basically 4 factors that affect toxicity of compounds. I factors related to toxicant. 2 factors related to exposure conditions. 3 factors related to subject. 4 factors related to environmental conditions. I factors related to toxicant. 1 type of salt form, e.g. barium sulfate poorly soluble, less absorbed, less toxic. Barium chloride highly toxic. 2 Nature and type of dosage form, depending on the nature and type, solubility differs and solutions are more soluble than emulsions. These are absorbed quickly and sustained released. Products are least water soluble and hence absorbed late. Solutions, emulsions, suspensions, capsules, tablets, sustained released products. 3 Composition of sample, impurities or contaminants present in product, e.g. 2,4,5-T herbicide. 4 Formulation and vehicle effects, e.g. BHC, DDT, pesticides, are more toxic if given in the oily vehicle. 5 Physicochemical properties of toxicant. Lipid solubility, higher is the lipophilicity, more is the toxicity. Polarity, polar compounds are less toxic than nonpolar due to their rapid excretion. Molecular weight, low megawatt readily absorbed more toxic. Protein binding, chemicals that are bound to proteins are less toxic or exerts delayed toxicity, depending on the nature and inherent toxicity of the chemical, as very less amount of chemical is in the free form. 2 Factors related to exposure conditions. 1 Dose amount of toxicant, e.g. large dose of NaCl can be toxic fatal, but very small dose of a potent toxicant no effects. 2 Route and site of exposure, GIT, oral PROS, PO, e.g. elemental mercury non-toxic oral route, highly toxic inhalation. 3 Schedule of dosage, single large dose more toxicity, however, 4 cumulative toxicant divided doses more toxic. Oral dose on empty stomach more toxicity. Cyanogenic glycosides, more toxic in full stomach. For duration and frequency of exposure, e.g. organophosphate insecticide, monocrotophos, in acute toxicity, anticholinesterase. Manifestations, i.e. salivation, tremors, convulsions. However, on repeated doses, delayed neuropathy is seen. Copper, repeated administration exhibits cumulative toxic effect. 5 Interaction of compounds. Toxicity of a compound may be different due to simultaneous or consecutive exposure with to another substance. In addition, an additive effect occurs when combined effect of 2 chemicals is equal to the sum of the effects of each agent given alone. 2 plus 3 is equal to 5. E.g. when 2 organophosphate insecticides are given together, cholinesterase inhibition is usually additive. B. Synergism. A synergistic effect occurs when combined effects of two chemicals are much greater than the sum of the effects of each agent given alone. 2 plus 2 is equal to 20. E.g., both carbon tetrachloride and ethanol are hepatotoxic compounds, but together they produce much more liver injury than the mathematical sum of their individual effects on liver at a given dose. See potentiation, when one substance does not have a toxic effect on a certain organ or system, but when added to another chemical makes that chemical much more toxic. 0 plus 2 is equal to 10. E.g., isopropanol is not hepatotoxic, but when it is administered in addition to carbon tetrachloride, hepatotoxicity of CCl4 is much greater than when it is given alone. E.g., chamomile tea may intensify or prolong effects of sedatives. The antagonism occurs when two chemicals administered together interfere with each other's actions or one interferes with the action of the other. 4 plus 6 is equal to 8, 4 plus 4 is equal to 0, 4 plus 0 is equal to 1. Antagonistic effects of chemicals are often very desirable in the toxicology and forms the basis of many antidotes. 6. Palatability may increase voluntary intake of a toxicant and increase its toxicity, e.g., flavored and paraffin-embedded rodenticides are used to enhance its intake palatability. 3 factors related to the subject. This can be better represented and understood by the following figure, Figure 4. Fig. 2. Host-subject related factors influencing outcome of toxicity, toxic effects. Look at the screen. Source, Relling, M.V. and Giacominni, Kilometer, 2006. Pharmacogenetics in Goodman and Gilman's The Pharmacological Basis of Therapeutics, pp. 94. 1. Gender, male mice highly susceptible to nephrotoxic effects of chloroform. Female mice as such no effect. 1. Age, young and old ones more susceptible. 2. Pregnancy. Pregnancy causes marked changes in the hormones and metabolic enzymes causes which influences toxicity of substances. High progesterone levels during pregnancy increase in the hepatic microsomal enzymes, which leads to increased susceptibility to pesticides toxicity owing to their rapid metabolism. 3. Lactation alters toxicokinetics of some toxicants. Enhances excretion of some toxicants, e.g., lipophilic toxicants DDT, PCB in the milk-suckling young ones. Consumers. 4. Body weight. Obese people require more anesthetics. 5. Stress leads to increased secretion of endogenous corticosteroids and other hormones. 6. Exercise helps maintain optimum levels of enzymes and hormones which can help in optimum metabolism and excretion of toxic substances. 7. Smoking predisposes individuals to toxic effects of several chemicals that might lead to metabolic disorders like cancer. Toxic chemicals in the smoke also causes cancer. 8. Genetic status. Gene-related alterations alters xenobiotic metabolism or tertiary receptor sensitivity, e.g., favism, hemolytic anemia on consumption of faba beans, Michelle faba. Related to deficiency of erythrocytic glucose 6-phosphate dehydrogenase, lactose intolerance. 9. Diet nutritional status, e.g., A. Starvation increases susceptibility to mycotoxicosis. B. With B and C deficiency increases damage from free radicals. C. Dietary deficiency of vitamins and minerals retard metabolic activity of several enzymes. 10. Disease. A hepatic disease, liver cirrhosis, acute and chronic hepatitis impaired biotransformation, metabolism, which can result into increased activity of certain toxicants like pesticides, and hence more toxicity. B. Kidney disease, decreased drug xenobiotic clearance causes slow removal of toxicant from body. Derangement of acid-base balance produces uremia causing alterations in tissue receptors, e.g., oxalates and heavy metals, mercury. C. Other diseases might affect kinetics of the toxicant and hence ultimately the end response. I. Cardiovascular system insufficiency, cardiac shock. 2. Neurological disturbances. 3. Respiratory diseases, asthma enhances toxicity of pollutants. 4. Factors related to environmental conditions. It includes following factors which affects outcome of the toxic response. 1. Temperature. 2. Atmospheric pressure and altitude. 3. Light and other radiations. 4. Relative humidity. 5. Environmental pollution. 6. Ventilation. 7. Management and social factors. 1.8 Methods used in safety evaluation. Risk assessment. Objectives of risk assessment. Protect human and ecological health from toxic chemicals. Balance risk and benefits, e.g., pesticides need to be used to increase food production to feed growing population. However, their use need to be controlled, regulated, so as to safeguard human health in such a way that they do not leave residues in crops, soil, water, etc. Set target level of risk, e.g., food contaminants and pollutants which could be invariably present in the food and cannot eliminated completely, are controlled by assigning them certain levels limits. Arsenic, lead, aflatoxins are allowed in the food at particular mRL. Set priorities for program activities. For regulatory agencies, manufacturers, environmental consumer organizations. Estimate residual risks and extent of risk reduction after steps are taken to reduce the risk. Food safety affects us all, and in our daily lives we naturally want to avoid food that puts our health at risk. So question arises, who evaluates what is safe to eat and what is not? What are their decisions based upon? An explanation can be found by understanding risk assessment processes. Risk assessment if a food or ingredient leads up to a decision on whether any legal measures should be taken in order to prevent harm that could be caused by eating a particular food and/or an ingredient and/or contaminant toxic chemical present in the food. Hazard and risk are terms that are often incorrectly used interchangeably, but they are in fact not the same. Hazard. Hazard is any biological, chemical, mechanical, or physical agent that is reasonably likely to cause harm or damage to humans or the environment. Or a hazard is any source of potential damage, harm or adverse health effects on something or someone under certain conditions. Examples of hazard are metal object in the floor, wet floor, microbial chemical toxin in food, contaminated food, etc. Risk. It is defined as the probability that exposure to a hazard will lead to a negative consequence. Risk is the chance or probability that a person will be harmed or experience an adverse health effect if exposed to a hazard. Risk is equal to hazard x dose, exposure. E.g., eating fluorides product, let's say, a baked item made from such flour, running on a wet floor. Eating contaminated food, food containing toxin. Thus, the lower is the exposure, in dose and duration, to a hazard, the lower is the risk. The process of gathering all the available information about toxic effects of a substance and evaluating it to determine the possible risks associated with the exposure, ways to minimize the risk is what constitutes the risk assessment. There are 4 steps generally followed in order to evaluate hazards and risks connected to a food and or ingredient and or contaminant toxin chemical present in the food. The 4 steps of a risk assessment are: Step 1. Hazard identification. Could this food or anything in it be harmful? Risk assessors collect and review the scientific data and identify biological or chemical hazards in the food. Step 2. Hazard characterization. Dose response assessment. What effects do the hazards cause at what dose level? The risk assessors evaluate scientific data to determine whether evidence is strong enough to demonstrate that a substance has the potential to cause harm. They study the nature of these health effects and also calculate a safe level of exposure. This includes identification of effect levels of chemicals, contaminant toxins, food ingredients and or food additives such as LD50, dose producing 50% lethality, LC50, concentration producing 50% lethality, at 10, dose producing 10% response, as well as NIES. Step 3. Exposure assessment. Who may be harmed and how? The amount and distribution of a hazardous substance, routes and locations that the population can come in contact with the toxicant are evaluated. Experts need evaluate food dietary intake information, how much of the food or ingredients or toxicants are consumed by the consumers in general and by the specific population groups, e.g., infants, children, adults, or subpopulations, e.g., vegetarians, vegans, and how much they are likely to be exposed to these chemicals in food ingredients under real life conditions, where both the dose and duration are considered. The exposure must be evaluated to determine if a hazard presents an actual risk. With increased exposure, the risk also increases. Thus, toxicologists evaluate acceptable daily intake, ADI, tolerable daily intake, TDI, and estimated daily intake, AB, of food ingredients to know the possible exposure. Step 4. Risk characterization. How likely is it that people will experience exposure at a level that can cause harm in real life? This step is basically an analysis and integration of the conclusions from the hazard assessment, the dose response, and the exposure assessment. This step also includes and evaluates characterization of susceptible population, age-wise, sex-wise, special physiological stages such as pregnant, lactating female, immunocompromised individuals, such as those receiving radiation, chemotherapy, etc., since such population group could be highly susceptible to the risk than the rest of the general population. The final step is to formulate a final conclusion on the level of risk. The previous steps are taken into account to calculate the likelihood of the food or ingredient causing harm, according to the nature of the hazard and level of exposure. The level of exposure that can cause harm is compared to the actual level of exposure that someone would experience in the real life. If the exposure level is higher than that which causes harm, there may be a safety concern for consumers in general of a specific population groups. 1.9 Application of toxicology in risk analysis, risk assessment, risk management, risk communication. Risk analysis involves risk assessment, risk management and risk communication. Let us understand in brief how toxicologists help in risk assessment. Please refer Figure 5. Look at the screen. Fig. 3. Risk assessment on the principles applications of toxicology. Source: Ayrton, D.L. and Gilbert, S.G., 2008. Principles of Toxicology. Incarcerate and adults toxicology. The basic science of poisons. C.D. Klassen, ed. pp. 11 to 34. The three main subcategories of toxicology are descriptive, mechanistic, and regulatory, even though each has distinctive characteristics, each contributes to the other, and all are equally important to chemical risk assessment. A mechanistic toxicologist is concerned with identifying and understanding the cellular, biochemical, and molecular mechanisms by which chemicals exert toxic effects on living organisms. In the risk assessment, mechanistic data may be very useful in demonstrating that an adverse outcome, e.g., cancer, birth defects, observed in laboratory animals is directly relevant to humans. For example, the relative toxic potential of organophosphate insecticides in humans, rodents, and insects can be accurately predicted on the basis of an understanding of common mechanisms, inhibition of acetylcholinesterase, and differences in biotransformation for these insecticides among different species. Similarly, mechanistic data may be very useful in identifying adverse responses in experimental animals that may not be relevant to humans. For example, the propensity of the widely used artificial sweetener saccharin to cause bladder cancer in rats may not be relevant to humans at normal dietary intake rates. This is because mechanistic studies have demonstrated that bladder cancer is induced only under conditions where saccharin is at such a high concentration in the urine that it forms a crystalline precipitate, Cohen 1998. Dose-response studies suggest that such high concentrations would not be achieved in the human bladder even after extensive dietary consumption. A descriptive toxicologist is concerned directly with toxicity testing, which provides information for safety evaluation and regulatory requirements. Appropriate toxicity tests in cell culture systems or experimental animals are designed to yield information to evaluate risks posed to humans and environment from exposure to specific chemicals. Descriptive toxicology is, of course, not divorced from mechanistic studies, as such studies provide important clues to a chemical's mechanism of action, and thus contribute to the development of mechanistic toxicology through hypothesis generation. Such studies are also a key component of risk assessments that are used by regulatory toxicologists. Regulatory toxicologist has the responsibility for deciding, on the basis of data provided by descriptive and mechanistic toxicologists, whether a drug or other chemical poses a sufficiently low risk to be marketed for a stated purpose or subsequent human or environmental exposure resulting from its use. The US FDA is responsible for allowing drugs, cosmetics, and food additives to be sold in the market according to the Federal Food, Drug and Cosmetic Act. FDCA. Similarly, in India, FSI allows, means, by way of different regulations and guidelines which are based on sound risk assessment principles that are evaluated by the scientific panels and committees of the FSI, food, ingredients, additives to be sold in the Indian market according to Food Safety and Standards Act, FSA, 2006. Food regulations are not intended to guarantee that all food is safe. Achieving that goal would be too expensive. Instead, food safety law is intended to reduce the risk of unsafe food. 2. Reduce the risk of unsafe food. Food businesses are urged to pursue the practice of risk analysis and its three components as it relates to food safety. 1. Risk assessment. 2. Risk management, and 3. Risk communication. Risk analysis framework could be understood by Figure 6. We have discussed the risk assessment in earlier section. Let us discuss the risk management and risk communication in this section. Risk management is a process distinct from the risk assessment which involves weighing policy alternatives in consultation with all the stakeholders, interested parties, considering risk assessment and other factors relevant for health protection of consumers and for promotion of fair trade practices and for selecting appropriate prevention and control options, that is, monitoring measures, etc. The management of food-related risks therefore involves balancing of the recommendations formulated by experts and resources of all types that social and commercial groups and manufacturers can set aside for dealing with these risks. General principles of food safety risk management. 1. Protection of human health should be primary objective in risk management decisions. 2. Risk management should follow a structured approach. 3. Risk management decisions and practices should be transparent, consistent, and fully documented. 4. Risk management should take into account the whole food chain. 5. Risk management should include clear, interactive communication with consumers and other interested parties in all aspects of the process. 6. Risk management should be a continuing process that takes into account all newly generated data in the evaluation and review of risk management decisions. Risk communication. Risk communication is interactive exchange of information and opinions throughout the risk analysis process concerning risk, risk-related factors and risk perceptions among risk assessors, risk managers, consumers, industry, the academic community and other interested parties, including explanation of risk assessment findings and basis of risk management decisions. Risk management risk analysis framework can be easily understood with the help of illustration given below. Figure 7. Look at the screen. Fig. 5. Risk Management Framework 1.10. Let us sum up. As you would have understood, food toxicology is a very distinct subspecialties of toxicology than others, largely because of the nature and chemical complexity of food. Food has thousands of chemical substances in addition to the macro and micronutrients that are essential to life. Toxicokinetics and toxicodynamics help us understand about how chemicals are going to be absorbed, distributed, biotransformed and excreted from the body, as well as help in understanding mechanism of toxic effects. Regulatory toxicology plays extremely pivotal role in ensuring food we are eating is safe. The regulator, FSI in India, look after the food safety by establishing safety of foods, food ingredients, and contaminants by means of various regulations and laws, e.g., setting up of TDI limits, MRLs, etc. Regulator brings about these regulations and laws based on risk assessment by adopting risk analysis framework. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.